out of the three biasing networks, the voltage divider bias gives the best bias stability. Okay, in the sense, whatever may be the changes in the temperature or changes in the Q point or changes in the beta value, once the Q point is set, it hardly moves from its set location, and that is called as improved bias stability. So this voltage divider bias offers excellent bias stability. So let's look at the voltage divider bias circuit. So first let us draw the circuit diagram. Now I would suggest you to draw the emitter bias first, then you can convert that into a voltage divider bias circuit. Okay, because emitter bias circuit we have already studied. So first let us draw the emitter bias circuit. Okay, so you have a collector resistor here, and you have a emitter resistor here. RE, right? And then you used to have a base resistor here. Okay, so instead of writing base resistor as RB, let us name this first base resistor as R1. Okay, so this is basically your emitter bias circuit. Three resistors, RC, R1 and RE, right? And let us also mark the terminals, base, collector and emitter. Okay. Now in case of emitter bias, what we do is we are going to add an additional base resistor between base and ground terminal, and that additional resistor is found somewhere here. Okay, so what we have done, instead of having one resistor just like an emitter bias circuit, what we have done is we have added the second resistor R2 between base terminal and the ground terminal. So the further analysis shows that the addition of or the inclusion of R2 will greatly enhance the bias stability. Okay, so let us try to analyze the circuit in terms of the current and voltage equations. Okay, now so what I will do in this format, the circuit is pretty difficult to analyze in the sense it looks as though on the input side you have loop 1 and loop 2. So normally we jump into applying mesh analysis. So applying mesh analysis to a transistor circuit is a very tedious process because transistor circuits have multiple currents: collector current, base current and emitter current. So in order to avoid applying mesh analysis, what we can do is we can use network reduction theorem called as Thevenin's theorem. So we need not apply mesh analysis. Instead you can reduce the network using a circuit reduction theorem called Thevenin's theorem. So once the network is reduced to a simple format, then you can apply the conventional KVL. So Thevenin's theorem basically used in circuit analysis whenever you encounter a complicated linear bilateral network. So it states that Thevenin's theorem states that any complicated linear bilateral network consisting of several voltage sources and current sources can be converted into a simple network consisting of one voltage source in series with the equivalent resistance, which is also called as Thevenin's resistance. Okay, so whatever resistors you are going to see, we are going to ultimately convert these resistors into one resistor, which is called as R Thevenin or equivalent Thevenin's resistance, and the voltage we will trying to convert is VTH, which is called as Thevenin's voltage source. Now how to find RTH and VTH? There is a separate procedure for that. Let us discuss that procedure. Okay, now before that, what I will do, I will convert this complex network into a simple network by splitting the power sources. Okay, so input side, let us concentrate first. So you have one base terminal, you have one collector terminal, and you have one emitter terminal here. Okay. So base terminal is connected to R1, right? So base terminal is connected to R1. Other end of R1 is connected to plus VCC. Plus VCC. And minus VCC, the negative terminal is always grounded. Right? So that is ground. Okay, and let us visit now R2. One end of R2 is connected to base. Is connected to base. Other end of R2 is connected to ground. Connected to ground. And on the emitter side, you have RE, right? So emitter terminal is connected to RE, and other end of RE is grounded. Okay, so this is your input side. And on the output side, you can see that collector terminal is connected to RC. Right, and other end of RC is connected to plus VCC. So let us keep a power supply voltage on the output side as well. And minus terminal of VCC is grounded. It is understood. Is grounded. So this is your simplified equivalent circuit. Once you have this simplified equivalent circuit, you will be able to apply Thevenin's theorem. Steps to apply Thevenin's theorem. First step is to identify the load. Identify the load. In case of common emitter configuration, you have seen that base emitter is the input terminal and collector emitter is the output terminal. So output terminal is nothing but the load terminal. So in case of voltage divider bias, when you say identify the load, you should identify the output terminals, which is nothing but CE side. So common emitter side is basically your load terminal, right? So what you have to do is remove the elements from CE side. Okay, so that's the first step. Second step is to find VTH, which is also called as Thevenin's voltage. So after removing the load, you have to measure VTH. So you can write a statement stating that measure the open circuit voltage across the load, right? So in first step, you will remove the load, right? So whatever elements you will find between collector and emitter, you will remove it off. And after that, you measure the open circuit voltage. This is very important. Open circuit voltage across the load terminals. And that open circuit voltage is VTH. Done. Third step is to find Thevenin's equivalent resistance, RTH. So how are we going to find RTH? So to find RTH, what we have to do is, if your circuit is consisting of any voltage source, so you need to short circuit voltage sources and open circuit current sources. So if at all your complicated network is comprising of, let's say, 2 voltage source and 2 current sources, then in order to find RTH, what you are supposed to do is you short circuit the 2 voltage sources and open circuit the 2 current sources. Now with respect to our circuit, if we revisit, so this is our circuit, right? If you investigate this particular circuit, what you see is that this particular circuit is comprising of 1 voltage source, right? That is VCC. So you should short circuit this power supply voltage VCC, and we don't have any current sources, so you can ignore the current source over here. Okay, all right. So let us try to find now the Thevenin's equivalent network. Okay, so steps I have written, you can revisit. Okay, so now let us apply these steps to the circuit under consideration. So first step is to, let me just remove the, write the, just remove the load. Right, so what do you mean by load? Load is nothing but CE side. Okay, all right. So after removing the load, the circuit looks something like this. This is RB plus minus VCC. This is R2, right? This is your base terminal. This is your collector terminal. And this is your emitter terminal. This is RE, right? And this is ground. Okay. Now, removal of load means whatever is present on the collector emitter side, you are supposed to eliminate, right? So this is your collector terminal and this is your emitter terminal. What I will do, I will eliminate all the elements which are coming in contact with the terminals, collector and emitter. So what are those terminals? Power source VCC, collector resistor RC, emitter resistor R. So we have removed the load. Okay. So after removing the load, you can apply step 2. What is step 2? Step 2 is to measure the open circuit voltage across the load, isn't it? So where is your load? Load was here between collector and emitter, which you have removed. So by removing, you have created an open circuit. You are supposed to measure that open circuit voltage. So this open circuit voltage we will consider generally as VTH or VOC. Okay. So TH stands for Thevenin. Okay, VTH. Upper side positive, lower side negative. So this is what you have to find. So how will you find VTH? Practically, it is pretty easy to find. What you have to do is you have to just connect a multimeter over here, right? Or a voltmeter. So voltmeter records the voltage. So basically, VTH is nothing but voltage measured across R2, correct? So this VTH is nothing but voltage measured across R2. So you can write VTH is equal to voltage across R2. So how will you find the voltage? Either using potential divider rule or using conventional Ohm's law. So let's say this is your circuit current I. So you can write I is equal to V by R. So what is V? V is VCC. And what is R? The total resistance, right? R1 plus R2. This is R1. Okay. So the total resistance is R1 plus R2. Right. So you know the expression for current. I is equal to VCC divided by R1 plus R2. Now you can find VTH. So what is VTH? VTH is equal to voltage measured across R2. So VTH is nothing but current into resistance. So I into R2. I into R2, which is equal to I. What is I? VCC divided by R1 plus R2 into R2. Into R2. So we have found the open circuit voltage VTH. Okay. So if you rearrange, you can give potential divider rule. You can give the shape of potential divider rule. So VTH is equal to main voltage into resistance across which open circuit voltage is measured divided by sum of the resistance values. Okay, so that's how you measure VTH. So use this formula to determine VTH. So done. Measurement of VTH is done. Now what is left? RTH is done. So what are you going to do for RTH? You are going to short circuit voltage source. Okay, so that is VCC. So you have only VCC in your circuit, right? So that you are going to short circuit. Okay, and there are no current sources, so you don't have to do anything with the current sources. So let us create the short circuit and let's see how it looks like. So this was your VCC. Okay, let me draw first VCC, and this is your R1, R2, right? And this is your base, and this is your ground. This is your ground G. Okay, you can write. Fine. So this is your VCC. Now, in order to find RTH, we have to short circuit the voltage sources and open circuit the current sources. We don't have any current sources, so you can ignore the current sources. What do you mean by short circuiting? Short circuiting means creating a low resistance path. So that means to say VCC you need to replace with a short wire. Okay, so that VCC becomes 0. So this is your short circuit condition. And measure the resistance as seen from the output terminals. So you have created the short circuit and observe the equivalent resistance as seen from the output terminals. In the sense, when you peep into the network from the output side, whatever resistance you will get, so that will be the RTH value. So basically, when you look into the network from the output side, you would see that resistance R1 and R2 are connected in parallel. Okay. How? So you have this resistance R1, right? So just for the sake of clarity, what I will do, I will shift this resistance over here. So this is R1, and then you have R2, and then you have the open circuit terminals, and then you are trying to measure RTH, right? So with the equivalent network, you can clearly observe that, see, these two ends are connected together and the other two ends are connected together. That is nothing but your parallel connection. So for a voltage divider bias circuit, your RTH boils down to parallel connection of R1 and R2. So what is the reduction rule? R1 into R2 divided by R1 plus R2, right? So let me write here, RTH is equal to R1 parallel with R2. Done? So a linear, bilateral, complicated network is being converted into a simple network using Thevenin theorem, right? And by applying Thevenin's theorem, all the resistors which were present in the network being converted to RTH, and the available voltage sources being converted to VTH. Okay. So once this is done, you reconstruct the network. In the sense, in first step you had removed the load, right? Now you insert the load. Okay. So this is the last step. Complete the network. So on the input side, you have VTH, right, in series with RTH. Right, see, I'm not going to write now R1, R2, VCC on the input side because we have reduced our R1, R2 and VCC into VTH and RTH. So on the input side, you have a Thevenin source in series with Thevenin's resistance. And then, and right here, insert the load. In step 1 you had removed a certain part of the network, right? So that you have to reinsert here, right? So that we will do. So this leads to the following network shape: plus minus VTH in series with RTH, right? And this is your base terminal. So you had removed certain elements from collector and emitter terminals, right? So that we are inserting it. So let me insert the transistor here, right? And this is where your emitter terminal was lying, and in series with the emitter terminal you have had your emitter resistor RE, right? And similarly, this was your collector terminal. In series with the collector terminal you have had your collector resistor RC. So we have inserted back, and finally you have had a voltage source on the output side, right? So that was VCC, and this is your ground network. You see now the circuit is very much simpler in nature, and you can mark the transistor voltages minus plus, and you can also mark the transistor output terminal voltage VC. Okay, now this is your Thevenin's network. Okay, Thevenin's network. Now the advantage of this Thevenin's theorem is that if you compare, if you do 1:1 comparison with emitter bias network, okay, I'll just write. So let's say whatever I have written in white belongs to voltage divider bias. VDB means voltage divider bias. Okay, and I will write some similarities using yellow. So this stands for emitter bias. Emitter bias. See, my aim is to make you to understand the similarities between emitter and voltage divider bias. In case of emitter bias, on the input side you have had VCC. In place of RTH you have had RB, right? That's it. Rest all the same voltage. There was emitter resistor, there was collector resistor, and there was VCC. So only difference is that in case of voltage divider bias, in place of VCC you have VTH, and in place of RB you have RTH. So that is the difference. Rest all remains the same. So you can now easily apply KVL on the input side to find IB. Similarly, you can apply KVL on the output side to find IC. Okay, so let us quickly apply the KVL and let us see what relation we are going to get. Okay, all right. So we'll mention the transistor currents, IB, IE, IC. So all the blue ones are basically currents. Okay.